Hello. This is part two of the recording for the horizontal alignment. Okay. Yeah. Just now we have I think we have covered previously the the Unicode methods to find the horizontal curve details. Okay. So we have looked into that, and then to find the horizontal curve details, and then we should give I will give you a tutorial to do it as well for to find the horizontal curve. Okay, now I want to look at the super elevations, okay, for the horizontal curve. Okay, we're not going to in the projects we will do the design for the horizontal and vertical alignment, but probably we're not going to the super elevations. Okay, so but in this part, the second part of the recording, in this there will be some simple calculations for the super elevations. So when you go around a bank, you usually you need to the outside lens. Okay, like for example, this is the inside lens, this a middle lens, and then this outside lens. The outside lens, as well as all the lens, actually need to be tilted, inclined, so that to provide the whatever the reaction, to keep the vehicle um, from being thrown out to the curve. Okay, so the maximum super elevation rates for use on a state highway are shown in table 2.9 and 2.10. Just now we have look at that. So depending on the design speed, 30 until like 130, maximum super elevations, all of them are 10%. So the minimum could be I think it's about let me see. The minimum is the super elevations. These are super elevation. Minimum is 3. Okay, 3%. Okay, maximum in this chart there are up to 12 the super elevations. But just now the one we saw is this one is 10. 10. Up actually say up to 12% may be approved for use in some situations. So for the lower speed, you could be if it's approved, can go up to 12%. Otherwise, it is the maximum is maximum is 10. Okay, the use of the normal crossbar, either like the i.e. minus 3% super elevations may only be considered when curves radii exceed the values given in table 2.7 here below. It means that the crossbar, the normal crossbar is that the two edges of the rod. Let's say it's a two-way two-lens rod. It will slope towards the two edges from the central line. So on either side of the central line, it will be a slope of in this case 3% slope in both sides. What 3%? What does it mean? 3% actually is 1 divided by 33.33. So that means it's one vertical, horizontal is 33.33. 1 divided by 33.33 times 100, that gives us the 3%. Okay, so normally the crossbar, it could be 2.5%, which is 1 to 40. One vertical, 40 horizontal. It could be as flat as no, as I think it's 3. About 3% is about 1 in 33.33. Okay, so that's the normal crossbar. So there are times that we may not need to super elevate the rod. Even we can maintain the normal crown. We call it the crown. which crown. So the crown is the normal. We call it this position of the pavement is called normal camber. Normal camber. Okay. So that mean the pavement is lopped to both sides of the edges, both edges. Okay? So this is the normal camber. So we could maintain that. You know, if we satisfy this condition in this table 2.7. So for example, you know, the design speed is 30 and then your radius is 200, then actually you don't have to provide super elevation. You can maintain that normal camber. If it's 40, if your radius is 350, then you could maintain the camber. If your speed is design speed is 100 but your radius is 2400 meter, then you probably you don't need to provide any super elevations. You just maintain the normal camber, and then so that means that with a big radius you can do without the super elevations. Okay, so but if anything, you know, if you design your design speed is 80 and then your radius is like 1000, then you need to provide the super elevations. Figure 4.15, 4.16, 4.17 must be used to determine the design super elevation required for set highway horizontal curves. So we look at the design speed. For example, we look at we don't look at the, let's say we design for 80k, but probably we don't look at the actual 80k. We look at the 85 percentile desired speed. Okay, 85 percentile desired speed. That means that we don't look for the 80, so that the speed could be lower. For example, let's say design for 80k, and then if your horizontal radius, if it's let's say 300, okay, horizontal radius is 300 meter, and then for 80k 80 kilometer per hour, actually your design speed is 74. I think it's 74. Yeah, 74. So even the design speed is 80k, but we look actually the design speed that we're going to look into, the 85 percentile speed is actually 74. So we look at this the next table here. So the different colors shows the design speed at different show the different design speed. So we got 20, 30, 40, 50, 60, 60, 70. Okay, 70. This is up to 70, and then for a small radius. But if you have a bigger radius, you know, bigger radius up to like 2000 meter, and then your speed go up to the green one is 120. So just now we said that 80 kilometer, but actually for the radius of 74, radius of 7, sorry, okay, let's say just now we said that the radius is 300 meter, the 85 percentile speed of 80k is 74. So actually we can look at the 74 is between the red and the green, so it's not red, so 70 and 80, between the yellow and the green. So between the yellow, this is 70, this is 80. Okay, so yeah. So the radius, so between the radius is 30, sorry, 300. The radius 300. So we go project the line up, and then 74 probably about here. So this point here. So the super elevation that is required for this 85 percentile speed of 80k, which is 74 here, actually is about 5.8. The super elevation need to be provided is at 5.8. Okay, so this how we can find the maximum super elevations for the various speed, okay, based on the 85 percentile, okay, of the speed. You know, we okay. So the axis of rotation. The crossbar is used on straight section of the rod to shed water. We need to have crossbar. The water can run to either side of the rod. You know, from the central line to the edge, and then from edge can go to the across the shoulder, and then to a table drain. Sometimes if for the urban rod, when go to edge, along the edge there will be catch pits. So the catch pit will catch the water and then go to the stormwater pipe. This crossbar, which commonly known as the normal crossbar, is usually away from the central line on two-length two-way rods and away from the median on the dual carriage way rods. So these are the crossbar. Okay, so this one is a rural rod. It has a shoulder here. So and then this okay, this is a dual carriage way. The dual carriage way, so that the rod just slope one direction. Okay, so the rod pavement just slope. The crossbar is 2% on either side, and then the shoulder, it has a steeper slope, is 4%. Okay, so and then go to the table drain. So the normal crossbar generally changes to super elevation when the horizontal alignment becomes a curve, except where the curve radius is very large, and adverse or normal crossbar can be used, i.e. -3% super elevation. So the crossbar, we said the crossbar, you know, it change to super elevation when the horizontal alignment becomes a curve. Okay, so except when the curve radius is very large. So when the curve is not, when the radius is not big enough, then we need to provide a super elevation. When the radius is as it is big, you know, as from this table here, exceed the minimum radius, then we don't need to provide the super elevation. Then there's no super elevation happening. Okay, so so the rod will be you will change, you will be elevated. Okay, so okay, so the just I think like this one, the rod will be sort of, you know, when you're approaching a curve, so it will normal camber, and then you have a crown removed, so the outside lens, it will be elevated to the level, the edge will be level with the center, and then you sort of tip upwards, so same crossfall as a certain point, same crossfall as the inside lens, and then go towards the full super elevations. And this full elevation will be can be obtained from the table just now I show you, from the what is the 85 percentile speed, and then you can go for the table, and then you got the radius, and you can find the maximum super elevation. And I told you that I think it's maximum is 10%. So normally it's probably is less than 10%. So for the two-length two-way rods, usually it, normally it will rotate around the center line of the rod. So it rotate the center line of the rod. So the outside, this is the outside rod. The edge will rise up, and then the inside edge of the this rod will go down. Okay, so it's rotating about the center line of the rod. So, and for the dual carriageway, so it has a two, it could rotate around both of these, either this or that. So it could, this one, they maintain the height of the edge. For the left hand rod, it maintain the left hand edge. Normally this rod is sort of it has a same crossbar across. It's a slope inside. Apparently the drainage is in between, in the median, so it's slope inside. And for the right land, you slope from the right hand side, from this side of the rod, you slope inside as well. So it will rotate upwards for the left hand side, and then going downwards on the right hand side. So it will sort of this is a central rotation at the edge, just the edges of the rod just next to the median. This is the median. Or certain rod, the dual carriageway, it could be, they have this normal camber. It's slope both sides, so they have a drain on this side as well, on the left hand side, and a drain on that side. But when there's going to turning right, I think the turning right, so the things are going up as well. From the right, the outside land, it will go up to level and then go further up, super elevations. The same thing for this right hand side as well. Normal, this normal camber, and then we will just go down, and then the super elevations, and there's a median. So it's rotate around the middle of the edge of this the median. So the median is maintain the height, maintain the level. Yep. Application of super elevations. The super elevation, the transition from normal crossfall to the maximum super elevation for horizontal curve on a two-way rod generally consists of a crown runoff and a super elevation runoff, as shown in figure 4.12a. So we have this thing called the crown runoff and super elevation runoff. Okay, so look at that. We have this from the from the normal camber with towards until the full elevation. The line should be aligned here. The line is not really aligned properly for this part. The whole thing from from this position until the full super elevation, this is called a super elevation development land. Super elevation development land from this position, the normal camber, to this full super elevation. But from this position where the outside land is level towards full super elevation is called a super elevation runoff. Super elevation runoff. Incidentally, this land is the spiral land as well. Super elevation runoff for this transition curve. Okay, so this is a spiral land. But for the circular curve, this point, this one is from the from this when this position, when the outside land is level towards full elevation. Actually, there's no definite point here, but it is 60% from in the horizontal curve. We have this called the TC, tangent to circular, or the other side will be the circular to tangent. So this point actually is 60% from 60% of the land, the super elevation runoff from the TC, and then towards full elevation, super elevation is still got 40% of the land to cover. So again, okay. So whether it's transition curve or the circular curve. So this one is called the super elevation runoff. Okay, so this is for the transition curve, or for the circular curve, this super elevation runoff. And the one, the distance from the normal camber to crown remove, for this one, the outside land is level, this is called the crown runoff. Okay, crown runoff. Okay, the normal situation on the dual carriageway roads is a one-way pavement which has a constant crossfall from the median towards the shoulder. The pavement is rotated at a constant rate to the maximum super elevation required by the horizontal curve, as indicated on figure 4.12a, b, and c. Okay, for if you have a dual carriageway, then we look at actually this one. This one is provided for both the 2 lanes 2-way roads and the 4 lanes undivided dual carriageway as well, undivided. Okay, so and then this one, the B, is the applicable to 2 lanes 2-way road also, but to interchange ramps and motorways. Okay, so this one is different, you know, the it's pavement rotate about the inside edge. For A is pavement rotate about central line. So this one is rotate about the inside edge. This one is rotate about the outside edge. So these are different variants for the rotation, and then which provide the super elevations. And the diagram is, these are the diagrams which need to be shown on the drawing as well. At the bottom of the this one, the long section. Okay, I think maybe I can show you that. I don't know whether I got that. Let me see. I think I don't have that. No. Actually, that one, if you go and look at the model under the I'm not this I'm not I didn't open the model. So inside they got the rod. I think the rod project. I think if you look at the plan and profile, under the long section, the bottom part of the long section table, they show the super elevation as well. If you look at that. Okay. The super elevation runoff. Super elevation runoff is the length of road requires to rotate the road pavement from level or 0% crossfall to the maximum super elevation rate required. So this is a super elevation runoff from this 0%. This one's 0% outside to the full elevation, full super elevation. It could be like 6%. On circular curve, the super elevation runoff should occur 60% on the tangent and 40% within the curve itself. The result in 60% of the full super elevation rates at the beginning of the curve. So this one is the one I show you just. That means at this point, this point here, TC on the curve, on the circular curve. So the circular curve, you've got TC, and on the other side you got this CT, so tangent to curve, and then from the other side is curve to tangent. So this one, this super elevation runoff will cover the whole distance, okay, from so the 2 point is that, you know, where are the 2 points? Left point here is 60% of the land from the TC, and the full elevation is 40% to the right of the TC. On transition curve, the super elevation runoff should normally occur over the planned transition land. Okay, so the TS to SC. So just now I think I show you transition curve. So the super elevation runoff for transition curve is from between TS and SC. Okay. Crown runoff is the length of rod required for rotate 1/2 of the crown rod pavement from normal camber to level, or 0% crossfall crown runoff to the at the same part used to apply super elevation cost. So the crown runoff is just this is a crown runoff from normal camber. This on the crossfall, it could be anything, you know, 2%, 2.5 or 3%, until 0. This one is flat, so 0% for the outside lens. Okay. Tangent runoff is a length of rod required to rotate a constant crossfall rod pavement. So this is a constant rod for when the rod has a constant rod pavement. So we call, instead of calling it the crown runoff, we call it tangent runoff. Okay, so that means that, you know, the rod here, that it has a constant crossfall. Okay, it could be like 2 lengths on both sides. So but it is constant, so it will be rotate the whole thing upwards. So instead of calling it the crown runoff, we call it tangent runout. Okay, so it's a bit tangent runout. Okay, so yeah, tangent runout. So that means that if it's you have the normal crown, normal camber, you know, you have the rod cross section, which is from center line, you stop towards the 2 edges. Then you, for that type of rod, we usually have this crown runoff. But if you have the rod which is if you got 2 lengths, you just slop in one direction, So that's constant crossfall rod pavement you across the 2 lengths. Then that from whatever the normal camber to the 0% when it's flat, you know, the outside edge and the inside edge, when it's level, is called the tangent runout. Okay. Super elevation development length. Okay. The criteria used to determine the length of the rod over which super elevation is developed. How do we do that? What are the criteria? Three-fold. So first is design speed. If you have 40 km/h, or you have 60 or 80 km/h, then it will be different. Okay, so we got formula for that as well. So the development length, if you have a higher speed, probably you need longer if you have a higher speed, probably your super elevation development length will need to be longer. Okay, that means that you need to have a longer curvature length as well. So that's a sort of is if you high speed, of course the radius need to be bigger. So if of course if your speed is lower, then you can have a smaller radius. Okay, so it's the design speed is it will determine the radius, or rather the radius will determine the design speed. You know, if you have a tight radius, then your design speed will be slower. If you have a big radius, then the design speed will be higher. So correspondingly, you know, if you have higher radius, so higher radius is correspond to higher design speed and also higher super elevation development length. The rate of pavement rotation, i.e. the vehicle occupant's comfort control. So it could the super elevation it could be determined by the rate of rotation. It could be 2% or 2.5% per second, or 3.5% per second. Thirdly, the relative grade between the inner and outer edge of the travel way, i.e. the appearance control. So we don't want this one to be the grade to be too high. On the flat terrains, you know, the outside edge is so high. It's not sort of aesthetically it's not very nice. So you don't want to go up too high. So that will design. If you don't go too high, they will you will control the speed as well. You cannot go that fast around that the curvature. Okay, so so this one you have lower speed, then you it will change the super elevation development length as well. So these are the three criteria which govern the super elevation development length: the design speed, the rate of pavement rotation, and the relative grade between the inner and outside edge. The super elevation development length must be long enough to ensure satisfactory riding quality and also give a visually pleasing road pavement. Okay, so comfortability, you know, the pavement rotation need to be kept to a minimum, and then visually pleasing road alignment. The inside and outside edge should not be too pronounced, too big, you know, too protruding in the especially in flat terrains. On a two-way road, super elevation development length is determined by the rate of pavement rotation. This rate should not normally exceed 2.5% per second of travel time of the design speed. However, sometimes we can go up to like 3.5% per second. Okay, sometimes, especially in the very low speed environment, if you travel in 30 or 40, or especially in the it's very monotonous, then you know the speed is lower as well. Divided roads are usually designed to higher standard and have wider pavement than two-way road. Super elevation on this road is developed over the longer of the length determined by the following criteria. Okay, so so for the divided roads, so that it could be a one single length as well. The two lengths are divided. We have such road like that. But this one is the divided road has a higher standard than the undivided road. So correspondingly, we need the super elevation. Then the standard will be higher. So for the divided road, the maximum pavement rotation is limited to like 2% per second. An appearance criteria which limits the relative grade, okay, between edge of travel to a value considered appropriate for the design speed. So the divided road will have a higher standard in terms of super elevation control. The minimum super elevation development length to satisfy the rate of rotation criteria for any road is determined by the following expression. Okay, so we have two formula. One is this one is based on the velocity, based on the first, the initial crossfall and the final initial slope and the final slope. Okay, and then the K here. The other one is based on the edge, is for divided rod. The based on the edge, the grade, the relative edge, relative grade of the two edges, for the divided rod. So that one, the G is the relative grade from table 4.5. So that one we'll have look later on this. So we look at the example. This one, the LE is super elevation development land. LE is equal to E1 minus E2, the whole thing bracket, time VD divided by K. So LE and L2 is cos 4 or super elevation at the ends of the super elevation development land. Okay, so E1, E2, that means that, for example, this one is E1. Okay, E1, for example, here is normal camber, maybe let's say minus 2.5% and minus 2.5%. So this one will be at this point, let's say assume it is 6%. So this one will be this one will be E1, this one will be E2. E2 could be like, this one is minus 2.5%, this one is plus 6%. Okay, so so E1, E2 is a cos for super elevation in the ends of super elevation development lands. K equal to this three value depending on the rate of rotation. If 2%, 2.5 or 3.5%, so 7.2, 9 or 12. Design speed, how much is the speed you travel? So this example shows just a short, that's okay, the super elevation development. E1 equal to plus 3%, and then E2 is minus 6%. Rotation rate is 2.5% per second, and design speed 70k. So you just plug into the formula, this one, 3 minus 6, because it's minus, okay, so 3 minus 6, the whole thing times 70 divided by 9 is 70. So the super elevation line, for that case, this one, is from here, from normal camber until the full super elevation is 70 meter. 70 meter. Okay, the minimum super elevation development land to satisfy the rod relative grade criteria for divided rod is determined by this. So another way to find the super elevation development land is by this another formula, equal to W time the holding bracket E1 minus E2 over GD. So the W here is the width of the travel way. So how wide it is, the inside, the E1 and E2 is cos for it. This one is the edge, so how wide is this the travel way? This one is, it could be like, this one is 2 lengths rod, it could be 6 meter wide, it could be 7 meter wide. So the W is the width of the travel way. E1 and E2 the same as before, the start of the super elevation development land and end of the super elevation development land. Okay, GD is the relative grade from table 4.5. So this table 4.5, if it's different speeds, let's say you travel at 50, then if it's depending on the how many lengths your is divided, for this divided rod is 1 length, 2 lengths, more than 2 lengths, you got a different value, 0.64, 1.28, 1.07. So that's G, that's the GD. What is that? GD. Yep, relative grade. So if you got 100, then based on whether it's 1 length is or 2 lengths or more than 2 lengths. Okay, so this is another way to determine the super elevation development land. Okay, so first way is based on the this formula, just the speed, and then the change of the crossbar from this initial camber to the full super elevation. Okay, and then this one K here is just depend on the rate of rotation, whereas the second case is more based on the relative grade from this from the travel way, Okay, I think that's all for the chapter all for this chapter 2. Okay, so this chapter 2.3, the geometric design of the rod. Okay, for this horizontal alignment. Okay, so yeah, okay, then so I will stop here now.